Sorry, guys, for the late start. Had a little bit of a technical problem here, but we're not too far off, only 5 minutes. So anyway, welcome back. A couple of things I want to mention, and looking at the schedule and what we had left over. Excuse me. Got a bit of a cough going on. Anyway, today is the 3rd, so we got here November 2nd through the 6th. We are doing pretty well as far as chapters are concerned. Chapter 13 is a very short chapter, probably about 14 slides or so. The one that is the longest is chapter 14. It's IMF, called the Intermolecular Forces. That one has about 30 some slides in that, so it takes a little bit longer. And the solution's extremely small too, probably 10, 11 slides. So of what we got left over, the chapter 14 is the longest one. Now, I have already previously mentioned that this coming Thursday, we'll make that a study day. I will be here regular time, and that's a good time for you to come in if you have questions, and we can go over the problems and so forth. If not, you're comfortable with where you're at, then, that's great. If not, come in with some questions. We go over that. Now, in looking at the schedule, right now, I'm tentatively probably going to make every Thursday a study day because, like I said, the chapters that we had left over are not that long. And the only one that take a little extra time, like I stated, is number 14. With that being said, that yellow, where originally we had scheduled to, because of the Thanksgiving holiday, have a meeting on Wednesday. You can cancel that because we're way ahead where we should be. So no, we won't. That yellow part for the week of Thanksgiving week, we will not meet on that Wednesday. Other than that, some people like the idea of having Thursday as an open day, and so that's a good time to catch up on where you're at. Some of you, I've looked through the homeworks, do have missing homework. The homework, the activities, those are still open. Yes, they're penalized for X amount of time. You get a certain percentage off, but getting some points is better than getting none whatsoever. So do go back in there and knock them out as soon as you can. Otherwise, eventually, I will put a 0 in there, and that could affect your grade. It depends. Homework, we do know that we dropped the lowest 2, but if you have a multiple of zeros, that could have a big effect on your grade. So keep an eye out. Keep in mind that Canvas sets your grade up based on things that have been graded, based on assignments that have been graded. So other assignments that are coming, obviously there's no grade to them. And you can do, I believe, a what if situation where you can go into your end of it and throw in a grade and see how your grade's affected. It gives you a kind of a what if situation. If I do well here and do well there, so forth. What we have coming up is on the week of the 9th, we have exam number 4, which would be chapters 10 through 12. Okay. And then the week of the 7th, which I believe is actually the 8th, Tuesday, we have them all on Tuesday. We have the final exam number 5, which is chapters 13 through 15. That following week, also that week, before I forget, the week of the 7th, you'll see there that if you are taking the lab final, you're taking the lab, you have the lab final. So keep that in mind. So that week you have the lab final, you have exam number 5, and then the finals week, following week. And
Quick
we
question.
have, yeah, go ahead.
Sorry, I don't mean to interrupt.
No problem.
So for instance, our labs are due Thursday. Would that mean that the lab final is on Thursday as well, or is there going to be a set time for that?
Well, that's a good question. I don't teach the lab, but I put it up here because all of us teaching 130, are teaching students are taking the lab and so forth. So it gives them an idea of what lab corresponds to the lecture. My guess, and I'll find out from my end, my guess is since all your labs are done on Thursday, they may have the same setup. But I would shoot a quick note to your instructor, lab instructor, and ask that question. But I'll find out from my end also, maybe make note of it here, kind of remind everybody. But that'll be my guess.
All right. Thank you.
No problem. No problem. Yeah, if anybody else have any questions, feel free to jump right in there and ask a question. There's nothing wrong with doing that. And so basically then the week of the 15th, again, we have our final, which, by the way, again, as a reminder, it is comprehensive. So it's going to encompass all the chapters. There is on the website a practice final exam, which is a good resource. There's also previous final exams from previous semesters that are a good resource. Now, bear in mind, those previous exams when we were doing face-to-face. So a lot of those exams we still utilize, but obviously we had to change the format a little bit, but the same type of question would be asked. I don't believe we have any type in your answer with respect to the final, where I have to go in there manually grade it, but I believe they're all going to be multiple choice or something along those lines. We are still working on it. All of us have taken a certain section of the final and developed questions for it. So all the instructors have touched all the exams and the finals. Okay. Any other questions, comments, concerns? Feel free to ask. I just kind of give you a heads up of where you're at because I know some of you are taking other classes, so I don't want you to get behind on work all in one class and forget about the other. So you got to find a happy medium there, a happy balance to encompass all of the courses that you're taking. Unfortunately, we're still going to do online next semester. So as far as I know, even the labs are going to be online. So if you're not taking the lab, you've got to take it next semester. Be prepared for online. I suspect all the other classes are going to be the same. I expect to be an online. Okay. Any other questions? No. All right. Well, yeah, I got one more here. Let me let her in. Let me go back to, excuse my cough. Woke up with a little bit of a cough this morning.
I have one question, actually.
Sure, go right ahead.
Related to what you're talking about. So, would there be any additional information that could be found about next semester, how it's going to work out? I've been trying to find stuff on GCC's websites to plan out how it's going to go.
As far as online or a hybrid or
Right.
Yeah. All I can talk, I do know that I have been assigned next semester's chemistry classes, and all of them are online with respect to chemistry. I can't answer that for the rest of the courses. I do know that at SCC, where I also teach, I opted for online. There are a couple of classes that are hybrid, meaning you go in there maybe once, twice a week. And that is still kind of up in the air. So
Okay.
up to this point, that's where we're at. I think we'll know more, right after the semester. As far as how that's going. What kind of classes were you talking about? Science classes or other?
Just the semester in general.
In general, yeah. There is a COVID page. Information page. I see if I can find it and I'll shoot it forward. They normally update that page periodically. Let me take a look. Sometimes also in Canvas, they'll tell you send alerts in Canvas, but
Okay, I just wanted to make sure because there were some physical events that were scheduled that never
Yes.
got to happen, and so I'm just kind of hoping that they'll still happen.
Yeah. Yeah. I think given the spike that's going on, it's tough. It's a tough call.
Yeah, thank you, sir.
Really, yeah, no problem. No problem. I'll find out from my end, see if I can get in more information, things in general. All right. So any other questions? No? All right, so we did go over this particular flow chart, but I want to go over it again because I need to emphasize the aspect of the mole. The mole is the common factor that we're going to find out when it comes to calculations of any type in chemistry. We cannot, when we say we got two reactants, A plus B, to give us C, for example, it's difficult to calculate if you start off with, let's say, 10 grams of A, try to calculate, well, how many grams of B do I need to get this reaction to go do what I needed to do? We can't go directly from grams to grams. So we have to go through a common factor, which is the moles. Now, the moles is simply nothing more than a number, much like the term dozen. We're all familiar with the term dozen. We think of 12 for the term dozen. Well, with respect to moles, it's the same thing, similar thing. I shouldn't say the same thing, in that moles is nothing more but a number. It just happens to be a number much, much greater than 12. Okay. And it's a gigantic number. It's Avogadro's number, and it is a number that's 6.02 times 10 to the 23rd particles, ions, atoms, molecules, bananas, oranges, whatever you're counting per mole. That's what it is. Just like we know there's 12 units per dozen. In the mole, there are 6.02 times 10 to the 23rd units per mole. Okay. And the other aspect is called the molar mass. Now, the molar mass is nothing more than adding up all the atoms in a particular compound. Now, keep this in mind. What we did, we started off with the periodic table. You recall, we went through it, determined who were solids, who were liquids, who were gases, and then we proceeded to talking about the electrons involved with respect to the elements, and then for some of these elements, with respect to the number of valence electrons. Okay, and that's the number of electrons in the outermost shell. Now, based with that, given that information, and then given the fact that the driving force was to get that magic 8 around its outer shell, that octet rule, either by gaining or losing electrons, we proceeded from going from elements to ions, either positive ions because the metals lost electrons. And I emphasize metals because we know now that all metals lose electrons. And then the other end of the spectrum were the non-metals whose propensity was to gain electrons, and therefore giving them a negative charge. So then once we determined the ions, and we also learned about those metals that had a variable charge. Some, there are 16 elements that when they become ions have a known oxidation number, 16 of them. I call those the sweet 16. That meant that all the other metals had a variable oxidation state. And we went through examples like copper 2, copper 1, and a variety of different ones. They have a variable, and we have to designate those using the Roman numerals. Okay. Well, once we talked about that, we started to putting ions together. Keeping in mind that the negatives are going to attract the positive ions, so they're going to come together. And that we put them together such that we have sufficient number of positive and negative charges to cancel each other out to give us a net zero compound. And so we know that sodium has a +1 ionic charge. The chloride has a -1 ionic charge. So therefore, when I put them together to make formula sodium chloride, NaCl, I put them together as a 1-to-1 ratio. If, for example, I was going to put together barium chloride, I know that barium being a +2 would have a barium, the barium element would be in group 2A, has 2 valence electrons, and when it becomes ionic, being a metal, will lose those 2 electrons to give you a +2 charge. The chlorides being in group 7 will pick up 1 electron to give you a -1 charge. And then if I need to put the barium and the chlorides together, I know that I need to put 2 chlorides for every barium ion. And so we put a subscript to designate BaCl subscript 2 to designate 2 chlorides. Keeping in mind that we put them together in whole numbers. They're not half numbers. Okay. Well, with that, knowing that, we also talked about the atomic weights of all the elements. That was that number underneath the symbol, which represented the atomic weight for all the isotopes of that element. And, excuse me, those numbers were not whole numbers, but actually were decimal numbers. For example, carbon has an atomic weight of 12.01. Now, the reason it has a decimal number, it is because it is the sum of all the isotopes of carbon. So we talked about, carbon 11, carbon 12, carbon 13, carbon 14, all of them that are carbon. The only difference being is that they had an extra, a different number of neutrons. And they all had a different contribution to nature. And so if we take into account the contribution of each isotope, and we average out the number of carbon 11, 12, 13, 14, and 15, which, by the way, are whole numbers, we end up with an atomic weight of 12.01, which is a decimal number. And I stated, do not use the atomic weight of the element, because even though they're decimal numbers, they come from the average of whole numbers, which by definition, by default, they have an infinite number of significant figures, okay? And so the atomic numbers would not be a factor with respect to sig figs. So when we get to molar mass, once we put all the atoms together, we get the atomic weight of each element that contributes to that formula, and we end up with the molar mass. And we call it the molar mass because the units are grams per mole. Grams per mole. The units of Avogadro's number is units per mole, okay? All right. Now, the other aspect was, and only under the conditions of STP, which is standard temperature and pressure, meaning that the standard temperature is 0 degrees Celsius, which is like freezing. That's the freezing point of water. And the pressure was the units of atmosphere, 1 atmosphere. Right now in Arizona, we're approximately 1 atmosphere. So that gives you an idea of what atmosphere, how much 1 atmosphere is. You also may find it to have units of millimeters, which is 760 millimeters. Anyway, if the pressure were to go to 3, 4, 5 atmospheres, you could definitely feel that pressure on you. So at STP, and only at STP, and only for gases, okay, gases occupy a volume of 22.4 liters for every mole. So we can have another relationship that we can utilize, which, by the way, is another ratio, liters per mole or moles per liter, okay? So that being said, is the only way, if I start with grams and I want to get to units, how many grams go to units, I have to go through moles. The common factor here is moles. I cannot progress from the yellow volume to the blue-green color grams without going through moles or the gray color atoms, ions, or units without going through moles. And these three conversion factors, okay, the molar mass has, it didn't show it here, but let me type it very quickly. With respect to units is grams per mole for the molar mass, okay? And so we have these ratios that, if you recall, when we did those chapters in conversion factors, I emphasized the ratios. And like we had 1 inch is equal to 2.54 centimeters. I can write it with centimeters in the numerator or centimeters in the denominator. Which one I needed depended on the units that I was looking for. Generally, the units that I'm looking for would be in the numerator. Not generally, always. If I'm looking for whatever units, I'm going to end up the units I'm looking for in the numerator, because the denominator, I'm going to set it up so they cancel out. Okay, so this one gets you from grams to atoms, or grams to volume, or vice versa, but you got to go through moles. Okay, and clear this up a little bit. And so we went through this scenario, this example, where we want to know, if I have 17.35 liters of a neon gas, what does it weigh at STP? Okay, and so using the method we talked about, the one name was dimensional analysis, we first write down what we're given. Well, we're given 17.35 liters. And I gave you the answer here, but I also, what I meant to do was put down the units that I'm looking for. Okay. And so that gives me a target. It gives me an idea. What am I looking for unit wise? So that allows me to work my conversion factors in the manner such that I can set them up so that when I do the mathematics, my units will cancel, leaving me with units of grams per, or grams of neon, which is fine. The question is being asked, what is the mass of the gas, neon gas, if I have 17.35 liters? And so I need conversion factors. I know I'm at STP because the problem gives me STP. If they didn't give you the letters STP, they may mention 0 degrees or 1 atmosphere. If they do that, then you know you're at STP. If that information is not given, you cannot calculate it. Remember, gases normally don't have a volume. We went through the properties of solids and liquids and gases. Gases, they occupy whatever volume the container they're in, except at STP. At STP, they all have 1 mole has a volume of 22.4 liters. So our first factor here gets rid of the liter units and gets me into moles, because, like I said, to get from liters to grams, I got to get to moles. And being an STP, my liters cancel, leaving me with moles, which is what I'm looking for to get to eventually grams. The other factor is my molar mass, because remember, the molar mass has units of grams per mole. And so once I'm in moles and I want to get to grams, I need the molar mass written with grams in the numerator, because my moles cancel out. So you think about it, if you have moles and I want grams, I multiply by the molar mass. If I have grams and I want moles, guess what? I divide by the molar mass. Okay. So that being the case, then I check this out, check my units, make sure my units cancel out, then I'm good to go. Now the math is up to you. And you plug that number in the calculator. I noticed something with respect to sig figs. I end up with 3 sig figs. Sig figs don't go away. We use sig figs throughout science, okay? So we have 3 sig figs. Now, the molar mass, as I stated, it is not used to determine sig figs because they come from an infinite number of significant figures, because they come from average of whole numbers, okay? So molecular weight, atomic weight is not utilized. We start off at 17.35, that's 4 sig figs, but then our next conversion factor is 22.4. That is a measurement, okay? Remember, any type of measurement is involved with significant figures. Why? Because any type of measurement has a degree of uncertainty. There's nothing 100%. When you measure something, either the length, the weight, or the volume, you will never ever get to 100% accuracy. Why? Because there's always an error involved in the last digit, and you're limited by the accuracy of the instrument that you have. Okay, so you may have, if you're measuring the length with the laser beam versus measuring the length of the meter stick, both of them have degree uncertainty, and both of them have a certain different number of significant figures. All right, so now that gives us that if you occupy, if neon gas is at 0 degrees in a 1 atmosphere, it has a volume of 17.35, which tells us the gas weighs 15.6 grams. Okay. Second part was, well, how many atoms? Okay, so I set up the same system. Okay, and I set up what I'm given and looking for units of what these are the units that I'm searching for. Again, I need to set up something to get rid of the liters to get me into volume. The fact that we aren't SPP tells us that we can use that relationship again. This time, because I'm looking for units of atoms. Good question. That is correct. 22, Nathaniel, 22.4 liters is not an exact measurement. Okay, it's a measurement. And therefore, with any measurement, there's a degree of uncertainty. All right. Yeah, so I look at my units here, double checking, making sure that everything cancels out like they should. I got liters canceling out like the beginning, like the first one. My moles cancel out, and using Avogadro's number now with atoms in the numerator, because that's what the questions ask me, how many atoms. Okay, I need atoms in numerator. Now it's a matter of doing the mathematics, using the scientific notation to input that Avogadro's number, multiplied by 17.35 and divided by 22.4. There you go. That gives you how many atoms you're going to have. All right. Now, if you look at the mathematics of this, you might ask, well, does that number make sense? 4.66 times 10 to the 23rd, which is much less than Avogadro's number, right? Well, yeah, that number makes a lot of sense because, you know, think about this. I only have 17.35 liters. And that means that I have much less than 22.4, okay? Which also tells me, if I do the calculations, that I have less than 1 mole of neon gas. So I have a number less than 1 when I divide 17.35 divided by 22.4. So that number multiplied by Avogadro's number is definitely going to give me a number less than Avogadro's number, okay? If for some reason you end up with a number much greater than Avogadro's number, then obviously you didn't set this up properly, because you should be getting a number less than Avogadro's number, simply because you're given 17.35 liters, which is less than 22.4. All right.
I have a question.
Sure, go ahead.
So when it comes down to significant figures, why does the second one have 2, but the first one only has 1? I mean, after the decimal, what I mean.
Oh, okay. I see what you're saying. No, because we're counting, when we count the significant figures, You go back and review your sig figs, okay? Because here we're not counting the decimal places. We're counting the digits that are significant. In the first one, the answer is 15.6, okay? There are three, the one,
Oh, okay.
the one, the
Okay.
5, you got it?
Yeah.
And
Okay. Now I figured out what I was
okay,
getting confused with.
yeah. You don't want to look at the decimal places. You want to look at the digits.
Okay. All right. Thank you.
That makes sense, huh?
Yes.
Okay, good. All right, good question. All right, then we talked about density. We did talk about density a while back, but basically it's another ratio, okay, which happens to be mass over volume. Now we can also extend that definition to incorporate molar mass over molar volume, which then allows us to calculate the density of gases at STP, okay? So we can calculate the density of ammonia gas, NH3, if we are at STP. First thing we're going to do is we're going to add up the molar mass, which means we're going to look up nitrogen. And there's one nitrogen at 14.02. Nitrogen is at 0.1. Then we got 3 hydrogens at 1.01 per hydrogen. So that gives us a total molar mass of 17.4 grams per mole. Okay. We are at STP, so therefore the volume is essentially just simply the molar volume, which is the 22.4 liter per mole relationship. We do the math, you can see how the units cancel, or the moles cancel out. Okay, so we end up with units of grams per liter, which is mass over volume, which is density. Okay, so this is good for determining the density of gases if you are at STP and at one pressure atmosphere. Okay, I think this is where we ended up, but we're doing the percent composition, which I'm pretty sure you're familiar with this already. Your grade, for example, for this class, excuse me. Your grade for this class is dependent on the contribution that every section brings to your overall grade. The homework has an X percentage. The activities give you an X percentage. The exams have an X amount. And the final has an X amount. So all together, they bring up 100%. We can do the same thing with respect to the percent composition of a chemical. In this case, they're using water. Okay, and so the first thing we got to do is to determine the molar mass of water. Well, actually, before you do the percent composition of anything, you have to determine the formula. Fortunately, we're aware of what the formula is of water, and that's H2O, 2 hydrogens, 1 oxygen. You go to the periodic table, you add up the atomic weight for the oxygen, atomic weight for the hydrogens, you should end up with a total atomic weight or molar mass for water as 18.02 grams per mole. Now, once you got that, excuse me, you take the contribution of total contribution of all the hydrogens, which is 2.02, and you divide it by the molar mass of the molecule times 100. Okay, and you do the same thing for oxygen, which is 16 divided by 18.02 times 100. And with this one, we should round it up to about 88.8. And so water, if you do an analysis of it, will always be 11.2% hydrogen and about 11.8% of oxygen. And that is true for water, whether you obtain it here or the other side of the world or on some asteroid someplace. Water has that formulation of H2O and will always have that contribution. Now, how can we do this with other molecules? This is a fairly simple one. Okay. How about this one? Anybody know what TNT is?
It's a very highly explosive, right?
Very high dynamite.
Yeah.
It, in fact, it comes from the name. Well, the symbol is TNT. C4 is better. Okay. Uh, Trinitrotoluene is the actual name for TNT. Okay. T for comes from tri, the N from nitro, and the other T from the parent structure of toluene. Now, we can determine anybody. Oh, here's another trivia question with chemistry. Does anybody know who discovered TNT? I'll give you a hint. There are prizes that are given out worldwide yearly for different things in the world. Nobel, exactly. Nobel was the one who discovered, and which is amazing, is that trying to make this in the lab is not an easy thing. There's three, what are called nitro groups, NO2 groups, and putting the first two is not a problem. It's that third one, the third nitro, that really is a challenge. And I just, as you know, as a graduate student, I wonder how many students have he had working for him trying to make this work, because they can get kind of crazy in the lab. I had a few explosions myself. Anyway, the formula is given to you. You got C7H5. Then there are three nitro groups, which means there are 3 nitrogens and 6 oxygens. Okay. With that bit of information, then we always go to the periodic table, the one that we give you. Determine the atomic weights. We got 7 from carbon. That's a total of 12.01 for each, a total of 84.7. There are 5 hydrogens, each at 1.01. Okay. 3 nitrogens, each at 14.01. And 6 oxygens at 16 for each one. So that gives us a total molar mass of 227.15 grams per mole. Okay, grams per mole. Imagine this. If you were to weigh out 227.13 grams of TNT, and hopefully it didn't blow up on you when you're dealing with it, you have 1 mole, 6.02 times 10 to the 23rd atoms of TNT. All right. So that being the case, once we get the total molar mass, we have the individual amount contributed by each element. So then we go to each one. Carbon had a total of 84.07 divided by 227.15 times 100. Hydrogen had a total of 5.05. Nitrogen total of 4203. Okay. And then oxygen at 9,600. So taking all those numbers, dividing by the total molar mass times 100 tells us we have 37.01% carbon, 2.2% hydrogen, and so on down the road. This is very legit. We do this in the real world. Every time I made a new compound in the lab, after we cleaned it up, got as pure as we could, we sent it off for analysis. Now, we had an idea of what general formula would be for the compound we made. Now that, coupled with a variety of different instrumentation, we verified that the structure, but one final thing was to send it out for analysis, knowing the general formula, like we have written up here, C7H5. That is the general formula. It doesn't tell you the structure at all. But we knew the general formula, and then you send out for analysis, and if it came out with the same numbers, then you're pretty much assured that that's the compound that you have, given the percentage of all the material. You send it off of copper, carbon and sulfur and nitrogen and oxygen and so forth, or any of the elements you needed. All right, so you might try these at home. It's a good test for you. We can bring back on Thursday when we meet for the meeting on Thursday being just a study day. If you didn't come up with these answers, we can go through it and figure out why not. So if you have how many liters will 3.425 grams of carbon dioxide occupy at STP? Okay, so you have the grams, you need to get to moles, and from the moles, you can get to liters, okay? So you need at least 2 conversion factors there. Here, the second question is, how many molecules are in the same number amount of carbon dioxide? So if you have 3.425 grams of carbon dioxide, right, you gotta get, you're still at STP, all these questions, STP for you. But even that, you don't need, think about this for a minute. The second part, it doesn't really make a difference if you're an STP or not, okay? Think about that for a second. The only one that does make a difference is the first question, the first question, number 1. And then the second one says, if you have 3.0 times 10 to the 15 molecules of carbon dioxide, how much does it weigh? And you come up with 2.2 times 10 to the negative 7 grams. That gives you a perspective. If you have that, that's a lot of molecules, 3.02 times 10 to the 15. But even if you had all those molecules, they're only going to weigh 2.2 times 10 to the negative 7 grams. Very small amount. As most balances wouldn't be able to pick that amount up. Gives you an idea of how small these carbon dioxide, these molecules really are. All right. Okay, so try that, and we'll go over that. There's questions if that's a question for you on Thursday. That being said, congratulations. We are 3 chapters away from finishing this semester. Okay, the end of chapter 12. Any questions?
I do, Dr. Fred.
Yeah, go ahead.
I had a little bit of a hard time with our homework last night.
Okay.
And I don't know. I didn't do as great as I thought I would. So I think I'm having a misunderstanding within those chapters that we were working on within our homework.
Okay.
So I wanted to say.
For the last chapter? For which chapter?
Yes. It was the homework chapter 10, 11.
Okay.
So,
well, go ahead.
No, go ahead, sir.
Well, I was going to say that'd be perfect. We can bring that in on Thursday.
Okay, that'll work.
Yeah, that's perfect because I'm sure there'll be other people who have questions about that, and that's a perfect thing. I can probably pull up the homework and we can go through it.
Okay.
Sound like a plan?
It sounds like a plan.
All right, sounds good. Anybody else? Any other questions about 10 and 11? Yeah, crucial because we got to make sure you understand those because we're kind of bringing them all together, and you can hopefully see here they're kind of tapped into each other, and like most course, if you don't get one part, then the other part makes it a little tough.
Correct. Okay, thank
All
you.
right, no problem. All right, we can do that. All right, no problem. Well, tell you what, let me jump into 13 for a little bit. And this is kind of helps even further, kind of ties in a lot of stuff together. Okay, now let me ask you a question here. We're going to talk bicycles. Like bicycles, what has it got to do with chemistry? Nothing. But it helps understand some of the things about chemistry. All right, let's say I have Okay, we have unicycles, two-wheelers and three-wheelers, okay? And so I have 1,000 unicycle frames, uniframes, right? Now, obviously, I'm going to need 1,000 tires, correct? Everybody
Yes.
agree on that? Yeah, of course, because I just simply have a unicycle here. Oh, that's supposed to be narrow. Now, with that being said, how many assembled unicycles am I going to have?
1,000.
Of course, 1,000, right? Okay, doing good. All right. Now, let's say we have 2,000 tires, biframes, two wheels, okay? How many tires am I going to need to assemble 2,000 biframes, two wheel?
4,000.
Exactly, okay? We're gonna need 4,000. Everybody agree on that so far? All right. Oops, sorry, didn't mean to spell. I forgot the rest of the word. How many assembled bicycles will we have?
2,000.
We're gonna have 2,000. Okay. Now, if I have if I have 9,000 tires, how many
3,000
tri-frame?
and 3,000.
You got it. Okay. So we got, everybody understands that. No problem, right? And we're gonna have 3,000 assembled. Okay. All right. That, ladies and gentlemen, is stoichiometry. Okay. Now I'm going to take out the tires and the frames and I'm going to start sticking chemical formulas in there. But the same principle applies. And the way we figured that, we knew we got tri-frames, you got 3,000 of them. We know that for every tri-frame, I need 3 tires. So whether I start off with 3,000 tri-frames or 30,000 tri-frames, I can calculate how many tires I need because I know that ratio of the tri-frame to the tires is a 1:3. And I know the ratio of the biframe to the tires is a 1:2. And the ratio of the tires in the uniframe is a 1:1. That is stoichiometry. Now, where do we get those numbers up front? That comes from that balancing these chemical equations. That's why when we talked about the chemical reactions, we try to tell you, for some of those reactions, we had a technique of how to balance it. The other ones, unfortunately, we do not. It's more of trial and error, starting with, a number here and then going to products, back to reactants, back and forth, and playing with the coefficient until such time that everything was balanced, okay? Once we got that balanced chemical equation, now we can use that information to calculate a variety of let me restate this carefully. We can use that information to do calculations with respect to chemical reactions. Okay, so all that what we just did with the bicycle frames is stoichiometry. All it is. It just so happens that we're going to deal with chemical reactions. Okay, Now we know that, well, we don't, but if you didn't know, if you take NO, nitrogen monoxide, and react it with oxygen, you get nitrogen dioxide. Okay. After we go through this scenario balancing, we put in the coefficients to balance it. So we have the ratio is 2 NOs per 1 oxygen to give us 2 NO2s. Okay. Now, I've been saying the molecules. If I have a molecule of this, how many of these? All right. Or if I did examples where I doubled and tripled the number of molecules. So in this example, if I have 10 molecules of NO, I need 5 molecules of oxygen for that reaction to proceed, because that ratio is a 2 to 1. And then if I use 10 molecules of NO and 5 of oxygen, I'm going to make 10 molecules of nitrogen dioxide. Okay. Now, instead of using the term molecules, now we're going to be talking about moles. And so that coefficients now will represent moles. It means that if I have 2 moles of nitrogen monoxide, I need 1 mole of oxygen, which then will react to give me 2 moles of nitrogen dioxide. Okay, moles. Now, I got a ratio here. I got a ratio between the balanced chemical equation where I have 2 NOs per 1 O. So I can keep track of that. Once I balance it, once I'm familiar with it, I can set that up. That ratio between reactants is written either like this, or I could put oxygen in the numerator. Like that, okay? Or I can look at the relationship between oxygen and nitrogen dioxide. And so I got oxygen per 1 oxygen per 2 NO2s, okay? There's another relationship. That is between one of the reactants and the product. And I can write that one with NO2 in the numerator and O2 in the denominator. Now I can utilize this relationship to help me calculate, because those are nice whole numbers. But what if I said to you, all right, what if I have 0.5 moles of NO? Okay. Well, how much oxygen do I need?
Would it be 0.25?
0.25. Okay, let's figure it out. All right. I know that the relationship in that reaction is 2 NOs per O2. Now, what units am I looking for? I'm looking for units of oxygen, right? So that relationship means that I need to leave oxygen in the numerator and divide that by 2NO. This relationship I just put in came from the balanced chemical equation. 1 oxygen per 2NO. Okay, it's understood that there's 1 in front of that oxygen. Remember that. It's understood there's 1. Okay, so now I can take that 0.25 divided by 2, and yes, you are correct. 0.25 moles of oxygen are needed if I begin with 0.5 moles of NO. Okay. Well, the question is, well, what if I need to know, well, how much of NO2 would I need if I start off with 0.5 moles of oxygen? You see now, I start off with 0.5 moles of NO. Well, how much of product do I get is the question. Okay. Now, what's my stoichiometric relationship between what I'm looking for is two NOs, correct? Per how many NOs, nitrogen monoxide? Two NOs. Isn't that from the balanced chemical equation? I got a 2 in front of NO2 and I got a 2 in front of NO. And so my relationship is essentially a 1-to-1. And so if I start off with 0.5 moles of NO, I will make 0.5 moles of NO2. Okay. So these questions that you're going to see, they're going to ask you about one reactant and one product, or one product and the other reactant. Your only concern about is calculating from what the questions are asking. What the other people are doing makes no difference. We have to assume they're in a sufficient amount of quantity. Nowhere in that question was there oxygen involved there. It just simply said, if I start off with 0.5 moles of nitrogen monoxide, how many moles of nitrogen dioxide can I make? And I just worry about the NO and NO2 and find their relationship, their stoichiometric relationship from the balanced chemical equation, which is 2-to-2. Okay. Now, looking at the next one, the formula is given to you, but it could be written out where it says, you know, nitrogen in the presence of hydrogen reacts to give you ammonia. With that information, you might be asked to write the equation from that information and balance it. And then you'll be asked questions like, well, if I start off with X amount of nitrogen, how much hydrogen do I need? Okay. So once I balance it, I know that 1 mole of nitrogen requires 3 moles of hydrogen, which will give me 2 moles of ammonia. Okay. Excuse me. And so if I had 1,000,000 moles of nitrogen, how many moles of oxygen would I need?
Can you say that one more time, please?
Now, if I have 1,000,000, let me put that down. If I had 1,000,000 moles of nitrogen, how many moles of hydrogen would I require?
3 million.
Exactly, 3 million, because the relationship from the balanced chemical equation is a 1-to-3. So whatever I start off with nitrogen, I need 3 times the amount of hydrogen for it to react in the correct ratio to give me exactly 2 million molecules of ammonia. Okay? So balancing the chemical equation is very crucial. And even before that, we need to put the correct formula down. You know, because here they could have said nitrogen monoxide reacts with oxygen to give you nitrogen dioxide. You have to be able to decipher what was written, and knowing that oxygen is one of the diatomic compounds, because if you don't know that, guess what's going to happen? Let's say that you wrote down nitrogen monoxide correctly, okay? And instead of writing O2, you wrote oxygen, and you also knew the correct formula for nitrogen dioxide, okay? And then you went to balance it, and what could you do here? What if you wrote it like that? Well, you can see where you can go wrong very quickly, okay? Without knowing that oxygen, remembering that oxygen was a diatomic, and that would be O2. Now, I've seen some of the problems that come up where you have to generate your own equation. They gave the activity, I believe the activity 7, where you've been asked to the reaction, for example, potassium and oxygen, giving you potassium oxide. Many people got it correct, but quite a number wrote oxygen simply as O, like I wrote there. Well, that would be incorrect because oxygen's diatomic. Okay. All right. So let us continue. What time is it? All right. So the stoichiometric coefficients, the coefficients give us the mole ratios. The mole ratios are crucial. Okay. All right. So if we look at this reaction, I'll stop it here. I won't go through it, but I want to show you how many ratios you can have. So here we have iron 3 oxide reacting with carbon monoxide to give us iron plus carbon dioxide. And it's been balanced for you, okay? And so here are the ratios that the first two examples they give you that relates the reactants. And you have the relationship of iron 3 oxide and carbon monoxide, which is a 1:3. You can write it with the iron 3 oxide in the numerator or in the denominator. Which one you use is dependent on what you're calculating, what you're looking for. And then the other relationship is the 2:3 relationship between the iron and carbon monoxide, okay? Now, you're not limited to that, those relationships, just through those two. I'll point these out. You know, we have the relationship of iron 3 and carbon monoxide, which we just showed. But you also have the relationship of iron 3 oxide with iron, which is a 1:2. And iron 3 oxide and carbon dioxide, which is a 1:3. Now, each one of these lines represent two ratios. So far we got 2, 4, 6 ratios that we can write that relationship. Okay. Then you have the relationship between carbon monoxide and iron. That's another 2. So right now you got 2, 4, 6, 8 ratios that you can write. And then you got carbon monoxide and obviously carbon dioxide. Okay, it's another 2 ratios with either carbon monoxide in the numerator or denominator. So you got 2, 4, 6, 8, 10 ratios that you can work with. And we're missing one more relationship. Does anybody see that relationship? We did the relationship between the two reactants, and then we did a relationship between each reactant and the two products, but there's one more relationship. And that
The
is
iron and the carbon dioxide.
you got it. This relationship here between the iron, solid iron, and the carbon dioxide, okay, which is a 2:3 also, okay? So that's another 2 ratios that you can write that in. So, you know, for this simple reaction, you got each line represents 2 ratios. You got 2, 4, 6, 8, 10, 12 ratios that you can work with if needed. Okay. And to get that, you got to make sure you have a balanced chemical reaction. Without it, then you can see if those numbers are not balanced, and if you try to do your calculations, that relationship we would assume everything's a 1:1. You can see that's not the case. It's a 1:3 just with the iron 3 and the carbon monoxide. So if I start off with 1 billion molecules of iron 3 oxide, 1 billion iron 3 oxide, I need 3 billion molecules of carbon monoxide, you know, for it. Now, this is a true statement whether I do small quantities in the lab or I do a big industrial plant and I do this industrial scale. That same relationship comes into play. It's just a bigger size. That's where the chemical engineer comes into play. Because in the lab, we can easily move 10 grams of iron 3 oxide. But if you're out with an industrial plant, the chem engineer comes in and tries to design a way to move 10 tons of iron 3 oxide. Totally different aspect. Anyway, what I want to do, I want to stop it here at chapter 3. And then I will continue with this the following Tuesday. The following next week, we would continue either with this chapter, or if there's questions about that exam, which is what, the 9th or 10th, I forget off the top of my head. If there's any questions about that, that will be the 10th. I'll be more than happy to answer any questions about that. But other than that,